what we're going to cover here is two Python packages that we use at California Policy Lab that we're experimenting with for ethnicity imputation. Now, as it was said before, this is in the private sector. We don't see this executed like very often, and this is because in the private sector we basically own the data because we own the platforms, the data through which the data is streaming in. So we decide what data to collect. Sometimes we will not be able to collect certain pieces of data, but most of the times we can collect like most of the things we want. Now in the public sector, it's going to be different. In the public sector, we are interested in the ethnicity of persons that reside in our databases, and this is because we are constantly monitoring for fairness, for biases, for equity. We want to offer, especially again in the public and social sectors, we want our services and our models and our algorithms to be fair and to be equitable, and that only works when we have knowledge of our clients or of the population we serve, of the ethnicity of the population we serve. Now, what is California Policy Lab? For those that don't know us, we generate research insight for government impact in the state of California. We have 6 areas of work. I particularly work in the labor and employment and homelessness spaces. And we have 2 campuses at UCLA, one at UCLA and one in UC Berkeley. Now, on to the meat of it. We're going to cover 2 models. There are more, but these 2 models are Bayesian models. One of them is called Bayesian Improved Surname Geocoding. It basically uses surname and a certain geography, either zip code or census tract, in order to infer or impute ethnicity. It is widely used in policy and regulatory work, as we're going to describe a little bit later. And there's a newer version. There's a rework of BISG called BIFSG. And this one adds first name to the parameters. And adding a first name aims to improve accuracy. It doesn't work sometimes. But it especially for ambiguous or cross racial surnames. And then you have the combined approach. So the combined approach is BISG gives you coverage but less accuracy, and BIFSG gives you more accuracy but less coverage. So what you do is you run BIFSG first, and then the null ethnicity that you end up having, you impute them with BISG. Right. So where are these 2 models used in, or where have we seen them like in the wild? We have seen them in the Consumer Financial Protection Bureau. They have investigated lending practices, and this is a credit card company giving details of their customers to this research group, but not their ethnicities. So they had to impute their ethnicities in order to investigate the unequitable lending practices that was seen in 2014. The Center for Disease Control and Prevention added ethnicity data for COVID surveillance. And this was, again, because as data was being collected by private entities, these entities are not allowed to collect ethnicities. So the CDC had to impute them once the data arrived onto their infrastructure. And also the Federal Reserve Bank of Chicago investigated racial discrimination in the auto loan market. Again, auto loan providers gave data to the Fed at Chicago, but they couldn't collect ethnicity because they were not allowed to. So the Fed had to impute the ethnicity in order to investigate their potential racial discrimination. What are the outputs of these two models? The output is a vector of probabilities. The probabilities is a vector basically of four distinct ethnic categories, and the probability, because the models are Bayesian, the outputs are probability of this observation of belonging to any of the 4 to 6 ethnic categories. And for example, we have Toby Ramos. Sounds like a baseball player, and that lives apparently in zip code 91335, and that when run through the any of these models being Bayesian, again, what we have is vector probabilities, where the high probability is that Toby Ramos is Hispanic. And then, for example, we have Tam Nguyen living in zip code 90005. Again, we have a vector of probabilities with the Asian probability, with Asian ethnicity being high. Right. So we need these are the models. Now, where these models are going must be applied to a data set. Our input data set is the data set Imputer. Imputer is a very famous commercial database in the US, but it is used mainly for mailing marketing. That is already introducing a bias. Because the observations contained in this database may have gone through some kind of selection mechanism that is introducing some kind of bias into the process. We don't know this bias. Being a commercial database, you're entitled to some kind of support, but that support doesn't include like asking questions about how the Imputer database was built. It has first names, last names, and addresses, and this requires us to perform some kind of post-processing when we bought that database, and we load them into our Postgres, into one of our Postgres instances. We need to do some post-processing. The post-processing is done by ArcGIS and needs to obtain latitude, longitude, zip code, and census tract. Now, a census tract, for those of you who don't know, I didn't know this. A census tract is smaller than a zip code, and is used. It's basically a geographic area that the U.S. Census Bureau uses to divide like the census effort. Now, in urban areas, a census tract is smaller than a zip code. So when we use a census tract, we have higher chance of being more precise, even with models that favor coverage instead of accuracy. However, for rural areas, a census tract is larger than a zip code. Why? Because a census tract is based on the number of people living on it, not the extent of the area or the surface it covers. In both, zip code and census tract can overlap. So in a rural area, you can have like a very large census tract that may contain one zip code and part of another. And in an urban area, you will have a very large zip code, and within you will have maybe maybe 2 or 3 census tracts and part of a third. So it's not a one-to-one correspondence. Now, we went through some stages of data preparation. We took data from Imputer, but again, we needed to have first and last names. We needed to clean those names because again, we have like some people reported their names as for example, Dr. Victor Von Doom, right? So we needed to strip that the doctor part. We also had like Jonathan Jameson Wilkinson III. The third we needed to strip. We needed also to have a valid census tract, and ArcGIS kind of missed some of the census tracts, so we needed to clean them as well. Zip code, we only filtered the zip codes that were not null and a valid social security number. This is the key, and this is why I won't be able to show you some of the code. I will be able to show some, but not the one that deals with SSN. Now, using the social security number, we're going to be able to link the Imputer data set, the subset that had a clean census tract, zip code, first and last name, with the data from the Employment Development Department, right? We're going to cover that in a bit, but for now, when we the entirety of the Imputer database consists of 82 million rows. Now, when we clean first name, last name, census tract, zip code, etc., we only ended up with 36 million. So the rest didn't have like a valid census tract, didn't have or had a null zip code, or maybe first and last names that couldn't be cleaned. So yeah, we're losing quite a bit. We're losing more than 50%. But for the exercise that we wanted to execute, this was fine. 44 are eligible for imputation, whereas the rest is not. Now, we have to run imputation. We are using this SIRGEO package and the ethnicity package. Both packages implement the two algorithms, the two models that we covered before. Both packages implement BISG and BFISG. They implement some other models, but these are the two that are mostly used in the setting that we're in, meaning in the public space, in the public and social sector. What is the output? The output is again a probability vector across ethnicity categories, as I showed you, and we further process the output to pinpoint a single predicted ethnicity, meaning whatever from the probability vector, we pick the highest one, and we consider that as the predicted ethnicity. We also add the model used to produce the imputation or the classification, that is either BISG or BIFSG, and the geocoding used to produce the imputation, either zip code or tract. And then just a Boolean flag, meaning that if the selected ethnicity was a high probability one, meaning over 0.85 probability. Now, we run this in a notebook, but this is the part that I'm not allowed to show you because we're linking social security numbers. We are showing those. I have those like in the clear, but don't worry, we have the appropriate like clearances. But we have those clear. They're not hashed, so I'm not allowed to show them. But I'm going to show you the results of the imputation. Now, this is not. We haven't at this point. We haven't linked the results of the imputation to the ground truth, right? So this is only the output of the models. Now, what we see here is that ethnicity package for the using the BISG algorithm and using a tract, census tract as a geography gives us an 88% imputation rate, and the imputation rate is basically how many non-null we managed to have. Meaning the model, how many records out of the 36 million ended up having a non-null imputation, right? And we found something else. The SIRGEO package, despite being older, did not implement the BIFSG algorithm with a tract geocoding type. That combination is not implemented in the SIRGEO package. So again, comparison is going to be like a little bit biased because we don't have that. We don't have those numbers. So there are going to be some hidden steps that, again, I'm not allowed to show you. First, we send this imputation file to the California Employment Development Department. They are the ones that link our imputations with the SSNs with their own data. This is workers from the state of California that have applied, for example, for unemployment insurance, that have a request of some kind of service. Give me a minute. That have been in contact with the EDD at some point in time. So they are the ones that do perform the linking between what we generate through the Imputer database and running the Imputer database through the models using those packages. And they take that and link that with their own data. Now, again, EDD will match our results with their ground truth, and they will send it back aggregated results because we're not allowed to see private identified information in their database like SSN. We have SSN, but they come from a database that we bought that is Imputer. But the EDD has SSNs that come from like real people, the population they serve. So we're not allowed to see that. Now, I am able now to show you a notebook. So I'm going to go through the notebook really quickly. This is the data that the EDT is sending us back. Now, from the high confidence flag to the left, it's the data that we send. Now, they link it and they aggregate and they send us back the columns on to the right of high confidence, meaning the race. Again, if you're working with this kind of data, please call it ethnicity. There are no races. There are no races in the world. This has been scientifically established. We have ethnicities. However, since this comes from an old database, I think they are using AS400, a mainframe, an IBM AS400 mainframe. So that's very old. So their column is called race. But yeah, we're not calling it that. We have race, the source system, and the number of individuals. Now we do some processing here. For example, this source, we have Imputer and unemployment insurance, and just unemployment insurance. What we are interested in is the subset of observations that are both in the Imputer database that we send and in the UI database that they have. So the intersection is what the population that we are interested in, and is really the only one that we can qualify. So what we need to do now is basically group and count, and we're grouping by the imputed ethnicity, the one that we have, and the race, the one that the California Employment Development Department has. And after this, we just filter out the ones that are the same. And this is going to give you like an idea of how good a job we did, or rather how good the packages that we used did. Now, this is something that I'm going to skip through this. These are confusion matrices, and the confusion matrices we're creating them by a combination of model and tracked, and also by the high confidence flag. But these are the confusion matrices with counts. And these are the confusion matrices with percentages. Now, what I want to highlight here is we can generate classification reports from scikit-learn without having a model. And that is really cool because, again, these are Bayesian models, and Bayesian models don't have, this is debatable, but my stance is Bayesian models don't have training. They have priors. And I forgot to mention this, but priors, the priors supplied to these two models by these two packages implementations are the 2010 census data files from the UN. So whatever you wish to infer with those packages is going to be constrained by the priors contained in the snapshot that was the U.S. during the 2010 census. Um, there are some other approaches that use 2020 census data files, but you have to purchase them. And again, in the social and public sectors, we often don't have that kind of money. But again, what I wish to highlight here is that we don't need to have a working model in our code to use the classification reports from scikit-learn. We only need to have counts, which is all what we have here. We don't even have like individual observations because we cannot, that would entail knowing the social security numbers from the employment development department. And we don't have that. We're not allowed to have that. So just using observed class, predicted class, and account, we can use the classification report. And with the classification reports, I'm going to stop sharing this notebook. And I'm going to go back to my presentation. Right. So we get these insights. So first thing you have to know is that we have a lot of white ethnicity predicted in the data that we send to the Employment Development Department. And by overrepresenting individuals that have the reported white ethnicity, basically one of the packages, Pi ethnicity, is achieving a higher F1 score, but it has a great amount of bias. Now, let me just go through each of the rows. Now, for Asian ethnicities, we have an F1 score of 0.78. And that is consistently, we get consistently high performance across all models and combinations of geographies from the Pi ethnicity package. We get better F1 score by using tract. Again, a tract is smaller than a zip code in urban areas. So this is apparently the combination of using first name and using tracts. We can identify better people that have self-reported their ethnicity as Asian. Now, for people from individuals self-reporting as Black, as belonging to the Black ethnicity, this is hard. We get a F1 score of 0.62. And again, neither of these packages and neither of the model, and I guess informed by the priors that we have, we're good at identifying individuals that have self-reported as Black. And it was challenging for all models, all packages. Neither of them, all of them were terrible. For the Hispanic ethnicity, what worked better was the Sergio, the BIFSG model, the one that uses first name, as implemented by the Sergio package, but using zip as geography coding. We get a 0.84 F1 score. And the reason for this is one hypothesis that we have come up with is that Hispanics in the U.S. Live in more in less concentrated areas that roughly match zip codes. Right? They're not concentrated in high density population areas. They're more spread out, so to speak. And then we have the white ethnicity. White ethnicity, the BIFSG model implemented by Pi ethnicity package, and using zip code performed better, way better, to identify people self-identifying as white. Now, this is something to note. The Sergio package implementing the BISG package without the first name and using track has a higher score of 0.86. But that model is heavily biased and not recommended. This is the model. This is the combination of model, package, and geography that basically says everyone is white, and that way it achieves higher accuracy. But it's cheating, right? Um, yeah, the classical precision and recall conundrum. Right. So gonna almost running up to the end here. Weaknesses. The models are entirely ineffective at identifying Native Alaskan individuals. We didn't even have them here. Oh, wait, we have it at the end of the table. But yeah, none of the models were able to identify Native Alaskan individuals. A substantial number of individuals in the dataset have null, meaning once we sent it to the EDD and we got back, many of them, many of the SSNs that we reported, for which we reported ethnicity, didn't match with what the EDD had. So since there wasn't a match, they were classified as null. When the models don't produce a high confidence probability for an ethnicity, their accuracy drops dramatically to just over 50%, meaning just a coin toss. So if the models were not sure, meaning if the probability vector didn't have the highest probability ethnicity reported in the vector wasn't of over 0.5%, it meant that basically the model performed a coin toss. A coin toss to choose the reported ethnicity, which is horrible, right? Some models, particularly within the Sergio package, achieve high overall accuracy by disproportionately predicting the majority class, meaning the Sergio package, the models within the Sergio package said everyone is white. And by doing that, it achieves high accuracy, but terrible precision and terrible recall. And again, Black ethnicity is poorly identified by all models and all geographies, with very low precision and recall, even in the high confidence group. So you may be thinking, why am I presenting stuff that doesn't work? Right. So we need stuff that works. Well, two reasons. Reason one being no finding, parallel finding. I'm reporting this and I am showing you this so that you don't make the same mistake. But perhaps, and more important, in a time of disappearing databases, you will need to do this, and you want to do it unbiased and in a way that gives you high, an acceptable precision and recall trade-off, and an acceptable F1 score. But you will need to do this because in this country, the current administration is for some reason disappearing databases. I'm not gonna get into the politics of this, but there are databases that we, the public sector and the social sector, we use, and we use them to increase the to improve the our services being equitable and fair. But without that data, we need to come up with ways to complete that data that is suddenly disappearing. And we need to do this in the public and social sectors like every day. But eventually you're going to have to do this as well. It doesn't matter what side of the political spectrum you lie on, you will need to do this. So you will want to do this in a correct way and in a fair way and in a way that is representative of the demographics that you're dealing with. That's it for me. Thank you very much.